Hi everyone, and welcome to our first video. So before I get into the content of this video, I just want to give you a couple of kind of recommendations for how I would suggest approaching the videos for this class in general. So I would really try to think of using these videos as kind of an active and even kind of interactive learning tool rather than just a passive watching experience. So, there are a lot of things that make online learning harder than in person, right? And I think most of us would probably prefer to be in the classroom rather than just watching a video. But one really nice advantage to watching these videos is that you can pause them. So that really allows you to kind of do things at your own pace, pause when you need to pause and make sure that you're really understanding everything as you go. So throughout the videos, sometimes I will explicitly ask you to pause the video. I might give you a sample problem and be like, pause the video and try this problem out yourself. Even when I don't ask you to pause the video, you can always do it. So I just think in general, anytime we're doing an example together in the video, you're going to get a lot more out of it if you pause the video, kind of start working on the problem yourself, and then press play again to see how things go, rather than just sort of sitting there and watching me go over the examples. Another thing I would recommend is, there are lecture notes provided for all of the videos, and the lecture notes are just exactly what you see me writing on the screen here. So those are good, but I think taking your own notes can be really beneficial. I know that a lot of students find that they just retain information better when they take their own notes. And then also, I'm not going to write down every single thing that I say. So sometimes you might need to kind of fill in some things yourself by taking your own notes. Okay, so those are my recommendations in general. Let's now get into the material for this video. So the focus of this video is going to be reviewing some facts from geometry that you should have learned at some point in your life, probably in like a high school geometry class. So, if you've taken a geometry class in high school, you know that there's a lot of details, a lot of different shapes you learn about and different theorems, and we're really not going to get into all of that detail. There's really only a handful of essential facts that you need to know from geometry in order to be successful in this class. So let's get into it. So we're going to start by talking about triangles. So I want to give you some kind of general facts that you should know about triangles. So a triangle, first of all, is a polygon, so a shape like this with 3 sides and 3 angles. One way that triangles are frequently labeled, and we'll be doing this sometimes in this class, is that you'll use capital letters to label the 3 vertices or the 3 angles of the triangle. And then across from each of these angles, you'll use the lowercase of the same letter to label the side across from it. So for example, I'm going to label this side with lowercase b because it's across from angle B. I'm going to label the side across from angle A with lowercase a, and the side across from C with lowercase c. So that's something that you'll see, a kind of a convention that you'll see us use in this class for labeling. Another thing we sometimes do is add these sort of marks here to emphasize the angles of the triangle, and we'll see some different things we can do with that notation as well. Okay, so first fact I want to remind you about triangles is that if you take the 3 angles in a triangle and add them up, it's always going to add up to 180 degrees. So the sum of the angles in any triangle, so regardless, we'll see a lot of different kind of shapes of triangles in this class, but regardless of what that triangle looks like, the sum of the angles in that triangle is always going to be 180 degrees. Okay, another fact that is going to be pretty useful for us in this class is the relationship between the angles and the sides. So notice if you look at this, the triangle that I drew here, which angle looks like it is the biggest angle? So this angle B looks the biggest, right? So the angle that is kind of opened up the most. And notice that this side B, is the longest side of the triangle. And then similarly, angle A looks like it's the smallest angle, And then side A is the smallest side. And so in general, it's always going to be true that the longest side is always across from the largest angle. And the shortest side is always across from the smallest angle. And that kind of makes sense if you think about it, just kind of looking at this example. You know, the bigger the angle, the more it kind of opens up and gives space for that side across from it to be bigger. Okay. So that's just kind of, you'll see later on in this class when we get into trigonometry that if you always remember that the longest side is across from the largest angle, and vice versa, that will kind of help you make sense of some things later on. A couple of other things I want to add here. So a couple of special types of triangles. One is called an equilateral triangle. So an equilateral triangle has all of its sides are the same length and all of its angles are the same. So it has 3 equal sides and 3 equal angles. And so each of those angles, maybe pause and think for a moment, what does each of those angles have to be if they're equal? Well, they each have to be 60 degrees, right? Because we know that they add up to 180. So an equilateral triangle, I'll roughly sketch one here. This won't be perfect. Looks something like that. I just want to show you a little bit of notation. So if you wanted to represent the fact that all of these angles are the same, you will commonly do it like this. You'll put this little kind of curve like I did on the other one, and then you'll make a little notch on it to represent that those 3 are all the same. And then similarly, if you want to represent that the 2 sides are the same, you can do that by putting a little notch on the sides, or sorry, the 3 sides are all the same. You can do it like that. And then there's one other type of triangle that is kind of similar, which is what's called an isosceles triangle. Oops, isosceles, no, I was right. An isosceles triangle basically just has 2 equal sides and 2 equal angles. And so the equal angles are the ones that are across from the equal sides. So isosceles triangles can look lots of different ways, but I'll just sketch like one example here. So it might look something like this. So in this case, if we wanted to use that same kind of notation, again, we could say like these 2 angles are equal. The third one is not, and then we could put these 2 notches here to say, okay, these 2 sides are equal. Okay, so that's it for just kind of general information about triangles. We now are going to get into talking about a specific type of triangle called a right triangle. So we'll see that right triangles play a really big role in this class when we get into trigonometry. So what is a right triangle? Well, first we need to define what a right angle is. So a right angle is a 90-degree angle. And we are going to get more into what angles mean, so what like 90 degrees actually means in our next video. But for now, just think of a 90-degree angle. It's like the corner of a piece of paper, right? It's like a perfect kind of, or a corner of a square, something like that. That is what's called a right angle. And so when you have a right angle in a triangle, sometimes you'll use kind of a box like this. So we saw on the other ones that, for angles that are not right angles, you sometimes just draw like a little curve like this. The little box represents that it's actually a right angle. So a right triangle is just any triangle that contains a 90-degree angle. So the nice thing about right triangles, there's a lot of nice things about them, but the main thing we're going to focus on in this video is something called the Pythagorean theorem. So you should have, I think, probably talked about this in your pre-calculus class, but basically the Pythagorean theorem is an equation that relates the sides of any right triangle. So the side lengths of any right triangle can be related using the Pythagorean theorem. So what does the Pythagorean theorem say? Well, before we write it down, let's label some things on this triangle so that we actually are talking about something here. So if we call this side of the triangle A and this side of the triangle B, and then this side here C, the Pythagorean theorem says that A squared plus B squared is equal to C squared. So it basically means that if you take the side lengths of these two sides that are perpendicular to each other, the two that are kind of on either side of the right angle, and square them and add them up, you get the same distance as the length of this longer side squared. And by the way, there are special names for these different sides of a right triangle. So for any right triangle, these two sides here, the ones that are perpendicular to each other, these are called the legs of the right triangle, and then the longer side is called the hypotenuse. So one thing that's kind of nice to know about right triangles is that because of that rule we talked about on the previous page with the angles and the sides, the right angle in a right triangle is always going to be the biggest angle. So why is that? It's basically because we know all the three angles have to add up to 180. And so if one of them is already 90, there can't be another 90 degree or bigger angle in the triangle, or else the total degrees will exceed 180, right? So we can only have one angle that is 90 degrees. And so that means that the hypotenuse, the side that's across from the 90 degree angle, has to be the longest side. So that again is something that'll be kind of helpful to keep in mind moving forward. So let me put a box around this because Pythagorean theorem is very important. Okay, so let's just do a little bit of practice with the Pythagorean theorem. So I would recommend pausing the video and trying these yourself. And then once you're done trying them, or actually, sorry, try them one at a time because I can't fit them both on the page at the same time. So pause the video, try this one, and then when I go to the next one, same idea. Okay, so we want to figure out what is the length of this missing side here. So let's label it with B. Let's call maybe 6 will be A, and then this missing side will be B, and then the hypotenuse in this case is 10. So if we go through actually solving this, so we would say 6 squared plus B squared is equal to 10 squared. So we would get 36 plus B squared is equal to 100. So if we subtract 36 from both sides, we get B squared is equal to, so 100 minus 36, that's going to be 64. And then we can take the square root of both sides. And basically, because we're talking about a triangle, we know that B has to be positive, right? When we're talking about an actual triangle, you can't have a negative length. And so B is going to be equal to positive 8. In general, if you were solving this equation, you would want to say B is plus or minus 8. But again, because we know we're working with a triangle, we can just say, okay, it's just the positive one. And so that is our missing side in this case. All right, next one here we have, again, we want to find our missing side. So this one, let's call our missing side C because it's the hypotenuse, right? Whereas in the other one, the side we were missing was was one of the two legs. So again, we just can plug this into the Pythagorean theorem. We have 2 squared plus 5 squared is equal to C squared. So we get 4 plus 25 is equal to C squared, or 29 is equal to C squared. And so 29 is not a perfect square, right? If you take the square root of 29, you don't get an integer, you don't get a whole number. And so in this case, we would just say C is equal to the square root of 29. And additionally, this square root can't be simplified, right? So typically when you have a square root, you want to see, is there a number that I can kind of a perfect square that I can pull out from the square root, 29 is a prime number, so we're not going to have any luck with that. And if you wanted to, you could type this into a calculator and see what you get. And what you should see is that it should definitely be longer than either of these two sides, right? That's kind of a quick check you can do to make sure you didn't make any mistakes, is just remember that it should be the longest side. Okay, so that's the Pythagorean theorem. We're now going to move on to talking about something called similar triangles. So similar triangles, I have an example of two right here. They're basically triangles that have the same shape as each other. And the way that we can kind of make this idea of the same shape more precise is that they have all three of the same angles. So looking at these two triangles that I have here, if you were to compare this angle and this angle, they're actually the same, right? If you were to kind of take the smaller triangle and lay it on top of the bigger one, you would see that those 2 points would match up with each other perfectly. And then similarly, this angle and this angle are the same. And then finally, our third angle and our third angle here are also the same. So similar triangles, or actually, let me phrase it this way. I'll say two triangles are called similar if they have the same three angles. Okay, so like we said, same three angles, they also have the same shape. And so there's another way to kind of describe this feature of them having the same shape. And that is by saying that their sides are proportional. So similar triangles, and I'll explain exactly what I mean by that in a moment. Similar triangles have proportional So what do I mean when I say proportional? I basically mean if you take the side lengths of one of the triangle and kind of compare two of those side lengths to each other, and then you do the same thing in the bigger triangle, you're going to get the same ratio. So let me make that a little bit more concrete. Let's call this side on the triangle on the left, let's call this side A1. And then I'm going to call the similar kind of corresponding side on the bigger triangle A2. And then I'm going to call this side on the first triangle B1. I'm going to call this side B2. So when I say that they have proportional sides, what that means is that if you take two sides, so for example, if you take A1 and compare it to B1 and figure out what that ratio is. So maybe, for example, B1 is half of A1, right? So maybe this side here is half the length of this side here. If you take that ratio and compare it to the similar triangle and you use the same kind of corresponding sides, you should get the same ratio. And we could have done the same thing with the third side, right? So if we wanted to, you could call this C1 and C2 and make another ratio. I'm not going to write them all down because there would be a bunch of different ratios, but basically the idea is the same. Any two sides, pick any two sides in one of the triangles, find the ratio, and that ratio is going to be the same in the bigger triangle. So again, just to kind of say that one more way, imagine that this side is half the length of this side, right? It looks like it could be about half. That means that in the bigger triangle, this side is also going to be the half the length of that side. So again, another way of kind of saying that these two triangles have the same shape. Okay, so let's do a couple of examples with actually working with knowing that triangles are similar and using that to find missing sides. So this is an example of three triangles that are all similar to one another, and we want to figure out what are the missing sides. So one of the triangles is all filled out, right? This one, we know all three sides. We want to figure out, what are all of these missing sides here. So I would recommend pausing the video and seeing if you can figure at least some of these out yourself. I think the first one is a little bit easier. But you can either kind of just think about what similar triangles mean, or you can go back and use this ratio idea and actually solve equations. So pause the video, try it yourself, and then we'll come back together and do it. Okay, so let's start with the first triangle. So we could set up ratios the way that I wrote down up here. So if you wanted to set up ratios, you could say something like 4 over 5 is equal to 8 over, and maybe we could call this side B. So 4 over 5 is equal to 8 over B, and use that to figure out what B is. And that's what we'll do on this example. So I'm going to save that method till we get to that example. The easier method for this one is just to recognize the fact that, okay, these triangles are supposed to be the same shape, right? And so if we compare these two sides, notice that the bigger triangle has a side that is twice as long as the smaller triangle. So if that side is twice as long, that means all the other sides also have to be twice as long, right? In order to maintain that same relationship between the sides. So that would mean that this side would have to have a length of 10, and this side would have to have a length of 14. And so we can check that with this whole ratio idea, right? We can say for the first triangle, we would have 4 over 5. And then for the second triangle, if we tried to compare those same corresponding sides, we would say 8 over 10. And those two fractions are equivalent, right? 4 over 5 is the same as 8 over 10. Similarly, you could do, 4 over 7 is the same as 8 over 14. So this one we could just kind of do in our heads by just saying, okay, in order to maintain that relationship amongst the sides, we're just doubling the lengths of all the sides. This third triangle, it's not a nice clean multiple of the base triangle, right? It's not just twice as big or half as big or something like that. It's kind of a weird other length. And so for this one, we actually do want to use ratios. So let's label these missing sides with B and C, and then we'll use ratios to figure out what those sides are. So the way we can set this up is let's start by finding B. So we can say 5 over B is equal to, and then we do the corresponding sides in the other triangle, 4 over 5. And so from here, we just have to solve this for B. So how would we solve this for B? Well, we can cross multiply, right? We can do 5 times 5, and we would get 25 is equal to 4 times B. And so this would tell us that B is equal to 25 over 4. And by the way, one thing that I would kind of tell you, I'm going to tell you right off the bat in this class, we're going to be using fractions a lot. And generally, I'm going to want you to write your answers as fractions rather than as decimals. So when you see a number like 25 over 4, resist the urge to go type it into a calculator. That's actually how I want your answer. You might also want to write it as like a mixed number. So you might think, okay, maybe I should write this as 6 and 1/4. Mixed numbers are actually kind of confusing. They just don't interact very well with other numbers. They don't, calculators don't really know how to handle them. So in general, leave your answer as an improper fraction, sorry. So yeah, we just found that B is equal to 25 over 4. Okay, so let me actually just color code that. It's bothering me. This is taking longer than I thought. There we go. Okay. So now we can do the same approach to figure out what C is, right? We can set up a ratio using whatever sides. And you could use 25 over 4, but 5 is kind of a nicer side length to work with. So let's just use that again. So here we can say 5 over C is equal to, and then we do the same ratio in the other triangle. So in the other triangle, it's 4 over 7. And so now, again, like we did on the last one, we can cross multiply and we get 35 is equal to 4 times C. And so that tells us that 35 over 4 is equal to C. And so we found that side C was equal to 35 over 4. So yeah, that is similar triangles. Again, these will come up kind of throughout the quarter, especially we'll be looking at similar triangles that are also right triangles, and we'll see those in another video a little bit later this week. Okay, so next thing I want to talk about, and actually this kind of fits with actually similar triangles as well. I want to talk about some special examples of right triangles. So it turns out that there are, if you know the angles in a right triangle, for certain angles within a right triangle, the sides have a nice relationship that you are going to want to basically memorize. So actually, out of everything in this video, I think that this is probably the most important part. You want to pay really close attention to this. It's going to come up like all throughout the quarter. So you really, really want to know what's going on with these special right triangles. Okay, so special right triangles, there's two different types that we're going to be focusing on. One of them is what's called a 45-45-90 triangle, or sometimes called also an isosceles right triangle. That's a triangle, just like how it sounds, where two of the angles are 45 degrees, and then the third angle is 90 degrees. And so this is an isosceles triangle, right? Because it has two angles that are the same. It also has two sides that are the same. So anytime you have a 45-45-90 triangle, if you know the length of one of these two perpendicular sides, I'm going to call it S, like S for side. Let's say that we know that this side has some length S. Well, that means that this side is also going to have the same length, right? Because this is a isosceles triangle. And then the hypotenuse is always going to have a side where it's the same S, that same number, whatever it is, multiplied with the square root of 2. So let's do a quick example of that, actually, just to kind of make sure we understand what that looks like in an actual example. So for example, if you have a 45-45-90 triangle, so I'm looking right now at this one here where it says 3 in blue. If you know that this side has a length of 3, well, then that means that this side also has a length of 3, right? Because it's an isosceles triangle. And then this hypotenuse has a length of 3 times the square root of 2. So no matter what this first side, whatever these two sides are, the hypotenuse is always going to be that same side length times the square root of 2. So that's one type of special right triangle. The other one is called a 30-60-90 triangle. And so again, it's a right triangle. It has one 90-degree angle. It also has one 30-degree angle and one 60-degree angle. And so 60 is 2 times 30, right? So it kind of gives this shape where the one of the angles is half the length or half the size of the other angle. So for this one, the relationship is a little bit more complicated, but let's say that you know that the shortest side has a length of S. Whatever the length of that shorter side is, the hypotenuse is always going to be 2 times that. So 2 times S. And then the other side is going to be whatever that shorter side is, S times the square root of 3. So let's do another example with this. So for example, looking now at this one on the right with the 2 on the bottom. So if we know that the shortest side is 2, according to the relationship up here, the hypotenuse is always going to be twice that. And so 2 times 2 would give us 4. And then the other leg, the longer leg, the one that's across from 60 degrees, that one is going to be 2 times the square root of 3. So one thing I want to point out, because I think a lot of students might kind of mix up what side is what in here. How can you remember which side is the hypotenuse and which side is the kind of longer leg? Well, remember that rule about the shortest side being across from the shortest angle and the longest side being across from the longest angle. So the biggest angle in this triangle is 90 degrees, right? And so whatever S is, if you take S and you multiply it by 2, that's going to give you the biggest side in this triangle. And so the biggest side is 2 times S, and that is across from our biggest angle. And then square root of 3, well, square root of 3 is less than 2, right? If you type square root of 3 into a calculator, you'll find it's 1 point something. It's definitely less than 2 because 2 squared is 4, so square root of 3 is less than 2. And so whatever S is, s times the square root of 3 is going to be bigger than s, but it's going to be smaller than 2 times s. So 2 times s is the longest side, it's across from the longest angle. S times the square root of 3 is the kind of middle side, it's across from the middle angle. And then s is the shortest side, and that's across from the smallest angle. So really important to have those relationships down. Okay, so I want to do one more example of finding the missing sides using these relationships. And these are actually, I know I already said that this is like the most important stuff in the video. I think these two triangles here with the labels in purple, these are actually like the most important single example in this whole video. Okay, so this is going to be a little bit trickier. We're now going to have to use the same relationships we had up here, but we're going to have to work backwards a little bit. So what's the difference? Well, when we did these two in blue, I gave you s, right? I told you, okay, we have 3 is the shortest side, and we were able to just say 3 root 2. And then in the second one, I gave you 2, and we were able to say, okay, 2 times square root of 3, 2 times 2. This one, I'm instead giving you the longest side. I'm giving you the hypotenuse. So we're going to have to do a tiny bit of kind of algebra and solving to figure out what the missing sides are. So let's start with the one on the left. So we know that these two sides are the same, right? They're both going to be s. So how can we figure out what s is using the relationship that we were given at the top here? And maybe pause the video and think about this. If we know that the hypotenuse is 1, and we're trying to figure out what s is, how can we kind of use these relationships to figure out what s would have to be if the hypotenuse is 1? Well, the hypotenuse is supposed to be s times the square root of 2, right? And so if we just say 1 is equal to s times the square root of 2, we can solve that for s, right? And figure out what s is. And so what is s going to be? S is going to be equal to 1 divided by the square root of 2. And so there's a slightly nicer way of writing this. It's kind of like a convention that when you have a square root in the denominator, usually you multiply the top and bottom by that square root, right? So if we take 1 over square root of 2 and multiply by square root of 2 over square root of 2, we would get square root of 2 over 2. But either of these is fine. You're just going to see this one on the right more often. Square root of 2 over 2 is kind of like the more traditional way of writing this. So we just found that these two other sides have lengths of square root of 2 over 2 and square root of 2 over 2. Maybe I'm just going to scooch this down a little bit because I want to circle these two examples before we move on. Okay, so let's do this next one. So again, we're now working in a situation where we know the hypotenuse is 1 and we're trying to figure out what these two missing sides are. So remember that for a 30, 60, 90 triangle, the relationship is that whatever the shortest side is, the hypotenuse is going to be twice that, and then the longer leg is going to be that number times the square root of 3. And so we could set up equations here, but I think this one we can kind of do in our head, right? So we know that whatever this side is, the hypotenuse is supposed to be 2 times as much. And so that means that this side has to be 1/2, right? That one is bothering me. There we go. 1/2. And then what about this longer side? Well, that side is supposed to be the shorter side times the square root of 3, right? Our relationship was s times the square root of 3. And so what is 1/2 times the square root of 3? Well, we can write that as square root of 3 over 2. So I'm going to circle these. Like I said, these are really important. These are going to come up a lot in this class. So what are these two triangles? They're basically just two examples of special right triangles, right? 45, 45, 90 and 30, 60, 90. And they're specifically examples where the hypotenuse has a length of 1. So you can have 30, 60, 90 and 45, 45, 90 triangles with really like whatever side lengths. As soon as you know one side length, you can always find the other ones just by knowing these relationships. And then this is just kind of one specific example for each of these. So, what do you need to know from this page? Basically, you're going to want to know this relationship here. You're going to want to know kind of the general rule relating the sides in a 45, 45, 90 and 30, 60, 90. So that's something that, I don't like to use the word memorize a lot in math classes, but that's something that you do want to memorize. Again, it's going to come super in handy. And then specifically, you want to know these two examples. Super important. Okay, so I want to briefly mention, I just kind of jumped right into this and I was like, well, it is what it is. Like, those are the lengths of special right triangles. And I didn't really explain why, right? And maybe that bothers you. It definitely bothers me to tell you something without explaining why it is the way it is. So I want to briefly try to explain it. So this is going to be actually kind of like a proof. But yeah, just want to kind of give you some understanding of like, why is it that the side lengths have these special relationships. So let's start with the 45, 45, 90 triangle. So let's say that we didn't know anything about the relationship between the sides. Let's say that we just knew that we were going to say this side had length S. So without even knowing the information I gave you at the top of the page, we already would know that this side had the same length, right? Because it's an isosceles triangle. You don't need to know special right triangles to get that. You just have to know that it's an isosceles triangle. So how could we find the hypotenuse? Well, let's call it C and use the Pythagorean theorem. So if we use the Pythagorean theorem, we would get S squared plus S squared is equal to C squared. And so that means that 2 times S squared is equal to C squared. And so if we take the square root of both sides, we're going to get C is equal to the square root of 2 times S squared. And again, we're not having to put plus or minus because we're talking about lengths. We know it's positive. And so 2 times S squared, or the square root of 2 times S squared, we can simplify that as the square root of 2 times S, which we earlier wrote instead as S times the square root of 2, but it's the same thing. So really this relationship I told you at the top of the page comes straight from the Pythagorean theorem. It just comes from the fact that these two sides are the same, and then we can find the third side using the Pythagorean theorem. Okay, so the one that the method for showing the relationship for the 30, 60, 90 is a little bit trickier, but I think it's actually kind of cool. So let's say that we take this 30, 60, 90 triangle and we put another one, an identical 30, 60, 90 triangle right next to it. I didn't do a great job. Let me draw that a little bit better. But while I'm drawing that, I want you to think about, what kind of a triangle is this going to give us if I take another 30, 60, 90 triangle and I just kind of stick it right next to this triangle? What kind of a triangle is that going to give us? So that's going to give us an equilateral triangle, right? Because the bottom angle is 60, and then we have 30, and then we have another 30. Together, that's 60. And so it's going to be 60, 60, 60. That is an equilateral triangle. Okay, so again, let's try to use the same kind of approach that we did on this one on the left. Let's say that we know that this side has a length of S, and that's all we know. We don't know anything else. We don't know any of the special right triangle stuff. We just need to use our picture and the Pythagorean theorem to figure this out. Well, we know that this side here would also be S, right? Because we put the same exact triangle side by side. And so notice that because this is an equilateral triangle, together this whole side has a length of 2 times S. Or that's not because it's an equilateral triangle, that's because we have S plus S. But the equilateral triangle comes into the fact that, well, this side is also going to be the same length, right? And so that means that this side here has a length of 2 times S. So why is it that the hypotenuse is 2 times the shortest side? It's because if you were to stick 2 of these next to each other, then you would see that the shortest side is actually half of the length of the hypotenuse. And then how do we find this remaining side? So, we have this extra triangle drawn here, but really we don't care about the extra triangle. We just care about this missing side, right? And so if I were to label this with the letter B and use the Pythagorean theorem, we can figure out what that side is. So using the Pythagorean theorem, we would have S squared plus B squared is equal to 2 times S squared. So that's going to be S squared plus B squared is equal to 4 times S squared. And that now if we move the s squared to the other side, we get b squared is equal to 3 times s squared. Now we can take the square root of both sides and we get b is equal to the square root of 3 times s squared. And then we can simplify this like we did on the other side, and we would get that b is equal to s times the square root of 3. And so that is why the longer side has a length of s times the square root of 3. So if you found this part that I just did a little confusing, that's okay. I would love for you to understand it, but at the end of the day, you really just need to know these relationships here. So if it doesn't bother you to not understand where it came from, that's okay. You can just kind of memorize them. But if you ever forget them, you can always go back to this proof and kind of use it to re-figure out what those side lengths are. Okay, so this is the last little bit of this video. So the last thing we're going to talk about is circles. So circles are definitely going to come up in this class. I would say they're probably not quite as important as triangles, so we're not going to talk about that much with circles. So what is a circle? A circle, the kind of geometric definition, is the set of all points that are the same distance, and I'm going to leave a little space here because I'm going to elaborate on what that distance is called, from the same point. So what do I mean by that? Well, if you take a circle and you kind of mark down where the center is, and I don't think I did the best job. That still doesn't look quite right, but close enough. So if you take the center and you measure the distance from the center to any other point on the circle, so like this, no matter where you draw that distance, it's always going to be the same, right? All of these blue lines I'm drawing have the same length. And so that distance is called the radius. So that distance is called the radius. And then that point, maybe I'll color code this, that point is called the center. Okay, so R stands for radius in this picture. So really the only two things that I want you to know for circles for now is what the area and the circumference mean, and then also how to find them. So the area of any shape is like the amount of space to fill it up, right? So you can think of the area as like if you were to kind of paint this all one color and measure how much paint you used, how much space is it filling up? And so how do you calculate the area of a circle? Well, you take pi and you multiply it with the radius and you square the radius. So pi times the radius squared. Okay, so what about the circumference? The circumference is measuring all the way around the outside of the circle. So if you were to take like a string and go all the way around the outside of the circle and then measure how long that string was, that is what's called the circumference. So you might be familiar with the word perimeter. So perimeter is a word that can be used for any shape to measure kind of how long it is outside of it. Circumference is the word that's used specifically for circles. And so the circumference of a circle is always going to be 2 pi times the radius. So I see students mix up these two formulas a lot. The easiest way I think to remember them is to think about units. So if you are measuring the area of something, what kind of units? Like what's an example of a unit you would use? Like for example, if you were going to measure the area of something, would your units be inches or square inches? They should be square inches, right? Because you're measuring a two-dimensional shape when you're doing area. And so that's why in the area formula, you're squaring the radius, right? Because the radius would be measured just in inches. You need to square that to find a two-dimensional measurement. Whereas the circumference, well, the circumference is a length, right? If you, it's like, again, taking like a string or a measuring tape and going all the way around, that's a length. And so that's why the radius is not squared in circumference. It's because you would just be measuring it in inches or centimeters or feet or whatever it is. You're not squaring that to find the circumference. Okay, so those are our two formulas. I want to just do a couple of quick examples, kind of practicing with these. So again, feel free to pause the video and try these out yourself. So the first one I want to do is just to find the circumference and area of a circle of radius 7. So to find the circumference, we would do pi times, we would do 2 pi times the radius. So that would be 2 pi times 7. And so that is 14 pi. So then to find the area, we would just do pi times the radius squared, which in this case is pi times 7 squared. So that would be equal to 49 times pi. Okay, one more example. This one is kind of asking you to work backwards. So let's say that now we know the area of a circle and we want to find its radius. So pause the video, think about this yourself, see if you can figure out what that radius has to be in order to make this true. So basically the best way to approach this is to use the area formula, but rather than use it to find the area, we can just use it to solve for the radius. Right? So we know that the area should be equal to pi times r squared. And so in this case, our area is 5 pi. So we can say 5 pi is equal to pi times r squared. And we now just want to solve for r. So we can divide both sides by pi, right? If we divide both sides by pi, the pi's are going to cancel out. And so we're going to be left with 5 is equal to r squared. And so again, so that would give us 5, or r is equal to the square root of 5. And you could check your answer by plugging it back into the area formula, right? If you do pi times the square root of 5 squared, that would be 5 pi, and that does match up with the area we found, or that we were given. All right, that is it for this video. Please check out the worksheet that is meant to go with this video. So basically, the worksheets are a way for you to kind of test what you got out of the video before you go and do the homework. So you don't need to turn the worksheets in. They're really kind of a low stakes way for you to practice before you get to the homework, which is actually graded. So I'll see you all in the next video.